Hey everyone, I'm Professor Turner with the Electrical and Computer Engineering Technologies program at Purdue University, and you're watching another video lecture series for ECET 273 Modern Energy Systems. Today's video is part 4 in our 4-part series dedicated to generators, which again are the devices that we use to produce electric energy in the modern electrical grid. In today's lecture, we're going to look at the technologies that are a little less common in the power system in terms of energy production, but that still contribute a small percentage to our generation portfolio. Particularly of interest today, we're going to look at the renewable energy technologies such as wind and solar that are available to us. So let's begin today's lesson by looking at the largest source of renewable energy on today's system, hydroelectricity. The production of electrical energy via the motion of water falling past the blades of a hydraulic turbine or a hydroturbine is just called hydroelectricity. In a typical hydroelectric plant, water is stored behind a dam feature which enables the water levels to reach great heights and store large amounts of potential energy. To produce electricity, the water is released from the dam to flow through a turbine to a lower elevation. The difference in elevation between the water level at the top of the dam and the bottom of the dam is called the head, and it's the primary variable that affects the amount of electric energy that a given hydroelectric plant is capable of producing. Therefore, we see that the purpose of a hydroelectric plant is to convert the kinetic energy of moving water into potential energy of stored water. This potential energy is then converted back into kinetic energy by diverting the stored water past a turbine. The spinning of that turbine converts the kinetic energy of the moving water into electricity or electrical energy. Several different types of hydroelectric plants have been developed and are utilized to produce electricity. In the simplest form, a stream or river is diverted to pass through a hydraulic turbine. However, designs like this are highly susceptible to changes in water flow due to daily and seasonal variation in the water table. A construction of a dam can mostly mitigate these variations by creating a reservoir or storage pond. However, such designs can still be affected by long-term weather patterns. In the most common configuration, the hydraulic turbine and associated synchronous generators are located at the site of the dam, although they can also be located downstream from the dam. In either case, the pipe used to divert water from the storage reservoir to the hydraulic turbine is known as the penstock. So here we have a schematic that represents the operation of this dam. We have a reservoir. This is either a lake that is connected to a stream or a lake that is just fed with small creeks or things like that. The difference between the level of the reservoir and the entrance to the penstock, again, is called the head. The penstock usually has some sort of grate over it to present wood and different matter from going into the penstock. Additionally, this is usually sluiced to be able to control the flow of the water into the penstock so that I can open or close the flow into the penstock. Really simply, all that happens then is water pressure from the top of the head pushes on the water at the bottom of the reservoir, forces the water through the penstock flow tube. That spins a hydraulic turbine. The water is then vacated into the river that is below the dam, and it just continues to flow throughout the United States watershed. That hydraulic turbine is connected to a generator inside the powerhouse that's then connected to the long-distance power lines. Often hydraulic dams can be used as sources of energy storage. To do so, water in a lower reservoir is pumped upstream with pumps into a higher elevation reservoir at night or weekends using lower cost energy from thermal plants during off-peak hours. During peak load, water is released from the upper reservoir and it flows through the mechanisms that we just showed to generate electricity. Often this generator turbine assembly in these plants can be run either as a motor or as a pump, so you don't actually have to have both separate units there. You kind of combine the function into a single one, and this equipment can kind of do double duty. This technique is called pumped hydro storage. Pump storage facilities produce electric energy from generation, but also clearly they consume energy when the water is pumped uphill. That takes electricity. So if we consider the total energy balance of such a system, only about 2/3 of the energy that we get out of the downward flow of water is reclaimed from the pumped. Sorry, only about 2/3 of the energy that we pump up is reclaimed. So we lose about 33% electricity in doing this. So therefore, the utility of pumped hydro facility is the ability to store energy for use when it's needed. It results in a net loss of about 33% energy, but it allows us to produce electricity from fossil fuel sources or baseload plants at low peak or low volume electricity consumption times, and then store it for production of electricity later times when we need it, like during the day.